When drawing mean charts in quality control, it's important to first recognize whether your situation is a mean chart with known variation or unknown variation. And the large beverage company scenario is a good test of that. Let's take a look. A large beverage company would like to use statistical process control to monitor a new bottling machine designed to load liquid into 350 milliliter bottles. Okay, this company knows that the exact amount the machine places in the bottle can naturally vary by a small amount, but does not have any, okay, here's our first hint. Does not have any more specific information about the process. First hint. Continuing on, the company operated this new machine under careful supervision, confident that the machine was under complete control for 7 hours. Each hour, a sample of 6 bottles. Oh, I want to note that to the size. Lowercase n is sample size. Lowercase n is the size of the sample. And we have just been told that each sample is going to be 6 bottles. Anyway, was taken off the line and the amount of liquid in each bottle carefully measured. This is the resulting data. So they took 7 samples. This was the average weight of the liquid with each sample. And here is the range. Oh, another important hint right here. Because how do you know if a situation is mean chart with known variation or mean chart with unknown variation? We had 2 big hints here. First off, it said in the paragraph that they didn't really know much about the exact natural variation as opposed to it being reported like a standard deviation in the process of some certain number. Okay. The other one was we were given information about range. When you don't know exact information about the variation in the process, you use range instead as a proxy. So just seeing that column with mean and then range of each sample is signaling this is mean chart with unknown variation. This is drawing charts with unknown variation. You say, well, okay, fine. Why do I care? Because then it depends. This dictates the formulas that you should use. Because look at the first question. What should be the control limits? What should the control limits be placed on the mean chart intended to monitor the machine in the future using the same sampling procedure that produced this data? That is the formula for mean chart with unknown variation. The upper control limit of a mean chart like that should be x double bar plus a factor called A2 times R bar. And the lower control limit, I mean, these are the actual formulas to set the limits it's asking about, should be x double bar minus A2 times R bar. So in order to answer this question and say exactly what the control limit should be, we need the numbers to put in here. Oh, okay, and we can get them quite easily from the data because x double bar, x bar generally means mean or average, so x double bar means mean of means. This is the average of the averages. X double bar is the average of the averages. So to figure out what x double bar we should be using in this particular situation, in these formulas, we just need to average these numbers here. Put them, each one of them, in your calculator, average them. I get an average of 351.013 milliliters. Okay. Now, we're going to need that for there and for there. We also need now R bar. Speaking of this table, R is range. Range is the largest observation in the sample minus the smallest observation in the sample. So in the case of these samples of 6 bottles, it would be the heaviest bottle minus the lightest bottle. R bar is average range. Oh, right. So we need that. Maybe I'll jot it here. R bar would be just average these numbers. I did that and I got R bar equals 0.743 milliliters. right? I'm just averaging these numbers. Oh, okay. So I have the number to put here and I have the number to put here. I just need to track down to answer this question the A2 factor. And that's again why it's important to recognize that this is that situation with unknown variation, because that tells you exactly what chart to find the A2 factor on. In this particular situation, we don't need a z-table. We need a chart that's specific to constructing control charts under this situation, where we look up A2. We look up A2. See where it says mean chart? A2, that's telling us it's one of these numbers. We look up according to the sample size. That's why I was so interested in that fact when they said their samples were of 6 bottles, because the factor we need in order to draw these limits is on this row, n equals 6, which means it's this number right here, 0.48. 0.48. I just need to remember that. You know, we're collecting up the numbers to use in this formula. We're almost done. A2 should equal 0.48. Oh, finally. Okay, we are ready to answer the question, because we'll say that the upper control limit equals, now I just piece it together, 351.013, right? That's that, plus A2, what we've just found, 0.48, times the average range, R bar, 0.743, and remember, do the multiplication first. So I get on my calculator that the upper control limit is essentially 351.37, right? When I do those calculations. Now the lower control limit, well, it's still 351.013. It's just actually minus. That's the only difference for the lower control limit. A2, so that's still 0.48 times 0.743, so I get 350.68. Now, this right here answers the question, because it asked where should the limits be placed. Right here. What would that look like? There's a little bit of room here on, this is the note frame itself, and it comes with the table bundled into the back. But there's also just some blank space here. So what would your mean chart actually look like in this case? Mean chart. Well, the center of the chart would be X double bar. So that's the 351.013. And ideally this would be like graph paper so that you could draw to scale. But basically there would be a upper limit, and that upper limit we have just determined should be placed at 351.37 milliliters, and then a lower limit, this is to plot future samples, that should be set at 350.68. So there we have a portrait of what the actual mean chart would look like. One hopes as if we were going to use this in practice, it would be somewhat bigger and it would have been drawn like with grid paper to scale. But I mean, that is what it would look like. Oh, all right. So anyway, we answered the first question. What's the next question? Where should the control limits be placed on a range chart intended to monitor the machine in the future using the same sampling procedure that produced the data? Oh, right. In the situation where it is a mean chart with unknown variation, you should really draw 2 charts. If it was a mean chart with known variation, there's just the one chart, a mean chart. But in this situation, you should draw a chart in order to plot future mean values, future averages of samples, and then another chart on which to plot future ranges, because you really ought to keep an eye on that in the future as well. Oh, and that's just another set of formulas. They're even simpler than the formulas we were working with. In the case of a range chart for this data, the upper control limit is just D5 times R bar, and we already know what R bar is. That's what I had calculated earlier. The lower control limit is D4 times R bar. Right, R bar is the 0.743 milliliters, the average of the ranges. So in order to answer this question and say where should we place these limits on this second chart, the only thing we need is D4 and D5. And how do you calculate D4 and D5? You retrieve them from the same table that's used for this purpose. That's what those other columns were. Here on the row for sample size equals 6, see how there's another column, it says D4, and in our case on that row there's a 0, and D5 there's a 2. Those are the numbers that we need. Okay, those are the numbers that we need. So I just need to piece that together now. The upper control limit here would be, okay, the D5 was 2. It was the outer column in that first chart, times 0.743. So I get basically 1.49. Okay, that's the upper control limit on the range chart. The lower control limit, I mean, you can write this out if you want to. 0 times 0.743. But 0 times anything is 0. So for this particular chart, the lower control limit would just be set at 0. If you wanted to sketch that, yeah, it would look like a second chart. You know, it would be your range chart. It would have R bar plotted on it as a form of a center line, 0.743, right? It would have a lower limit. Well, there isn't any way for a range to be anything less than 0, but we'll place the limit there anyway. And then an upper limit, that's what we just calculated. Let me make sure that this at least looks, even though I'm only freehand sketching it, kind of symmetric. It would be at, what's that, 1.49? And here's where you would plot future sample ranges in here. Now, before we leave this page, you know, I'm just using the blank space down here. I want to look back at this chart, this table that we've been using, and point something out. Okay, a very easy mistake to make in this problem. It might have been the reason why, if you had worked this problem earlier and couldn't get the answer, it might be why you're watching this video. Very easy mistake to make, watch out for this, is which row do I use on this table? Remember that when you want to retrieve A4 and D4 and D5 to put them in the formula, you're looking up the size of the sample. You're looking up, it says here, sample size. You never look up the number of samples. A very common mistake for a problem like this is a person might do everything right except they look up 7 and they use the row for 7. Why? Because there happens to be 7 samples in this table. There's 7 samples in this table. You don't use that information for anything. It doesn't go in any of the formulas, but it's a very common distractor. Remember, we're always looking up the size of the sample. Is it 6? Is it 20? Is it 10? We never look up the number of samples. Okay, anyway, we're not done with this problem. Seems to me there's one other question. All right, there is our, here we go, table. All right, this is finished because they just asked for the limits, but we even sketched it on the other page to take a look. And that might be handy. One of the reasons why I was doing that is because I knew that this question was coming up. A new sample is taken from the machine's output, and the exact weights of the liquid in each bottle, notice there's 6 of them, is that data point, that one, this one, this one, this one, and this one. According to the charts created in parts A and B, right, I sketched them, is this sample indicate that the process is in control? In order to use this information, this is a sample, but they're just telling us the 6 data points. We need to first determine the sample mean, which is to say the average of these numbers, and determine the sample range. Why? because then we're going to plot them on the charts. And if they fall inside the limits, we say, oh, that looks good, in control. And if they fall outside the limits, then we want to make a comment on that. We don't think this process is in control. But first, we need these numbers. Oh, all right. So, for instance, sample mean, the only thing that you do here is you just average these numbers. I did that. I got something like 350.19 milliliters. The only thing I did was average those 6 numbers. Sample range, I got 1.07 milliliters. Again, how do you find a range? It's really simple. You just look at the original data points, these 6, look for the largest number. Find the largest number on that page and then subtract out the smallest of the 6 numbers, and that's the range. Oh, all right. Now what? Now wait a minute. We were trying to answer a question and it said, according to this, do you think that the process is in control? All right, we want to take these values, these ones, and we want to mark them. Because we're thinking that, for instance, the sample range, we know that the sample range is 1.07 milliliters. That would, if you were to mark it on this table, you know, it would be like somewhere in here. Okay, 1.07. That's our sample, and it's inside the limit, so that's not raising any alarm with me. But notice that if you were to plot 350.19, the lower limit of the mean chart is 350.68. So that reading, 350.19, that reading is outside the control limits of the mean chart. It is below the lower limit of the mean chart. That right there is a signal that no, this process is not in control. That was a very lightweight sample. Something's going wrong here. The process is not in control. The sample mean fell outside the mean chart limits.